2, 1. All right, the next topic we are going to be dealing with is sound intensity. And sound intensity is talking about how loud or how quiet a particular sound is. Now, we know that sound is the result of a disruption of the air through an introduction of a push, some kind of power structure going behind it, whether it's the sound of a voice or the sound of an amplifier. So what we want to do is to be able to measure what that intensity is. So let's suppose that you have a sound being created, and let's put some kind of amplifier system here, and the sound is created from that, and as it travels, it goes in spheres away from the point. Let's say it's coming from some aspect here, and so we get these waves here that are resulting from this. Having issues in my smartboard. I'm going to kill my smartboard. I swear to goodness I am going to be doing that very soon. So, if I have some kind of spherical aspect to this, it's me going out in this realm, okay? So the sound causes a disruption in the waves, and that disruption carries on until some kind of not gravitation, but frictional air force is applying to it, to eventually die out. But let's say you're in an arena and you know it's not going to die out. If you hear this, if you're at a rock concert, and let's say that they're using a 50-watt amplifier, that's nice. Okay, now if you're standing right next to that sound, you will hear it really, really loud. You stand way back, a number of rows away from the stage, you're not going to hear it much, not nearly as strongly as you would if you were right up front, yelling and screaming and doing whatever. So, it gets dispersed according to the surface area of the wave. So it's this relationship here, and this relationship is what we call intensity, or I. And it is the power of the force of the sound divided by the surface area of the wave at any particular point. Well, we know in this case that this is 50 watts. But now the question is, how do we find the surface area? Well, what is the surface area of a sphere? Well, if you know your geometry here, you know that the ratio here is now going to be over 4 pi r squared, because that is the surface area there. So let's suppose that you were 5 meters away from the sound. So you're really up close and get the intensity of the concert. Then you plug that 5 right there, so this becomes 50 watts over 4 times pi times 5 meters squared. And this will give you then 50 watts over 314, round out to 3 sig figs, square meters. Okay? So, we're going to calculate that out. And we're going to find that this is going to be equal to 0.159 watts per square meter. Now, that's a pretty small number, so I think, well, that doesn't seem like much noise. Well, we actually need a point of comparison for this. And that point of comparison is called I sub 0, which is the absolute minimum intensity of sound that our ears can pick up under normal conditions. And that turns out to be 1 times 10 to the negative 12 watts per square meters. Now, you compare that to that, all of a sudden that looks like an extremely large number. And so if we were to take, now this is the intensity right here, so for that, we take that ratio, that is going to give us our values that we use in making this comparison. So if I divide that out, I get an answer of 1.59 times 10 to the 11th. And the watts per square meters cancel out, so this is just a ratio that we are using here. Now, the name of that ratio is named after the gentleman who did a lot of research dealing with sound. He was very famous in certain circles for his ability to deal with the deaf and working in trying to get them to be able to hear. He also developed a number of other things that became important later on, particularly in the assassination of James Garfield. He didn't assassinate him, but he was trying to help the doctors find the bullet within President Garfield. And so then he became even more famous because he's the guy who invented the telephone. So this is called this is going to be called a bell. Now, that will be because of his name, but for some reason, and I haven't done the research on this, and I probably should have, but they spell bell with one L instead of twos. Okay, so well, actually, this value is they're going to take the log of this, and that's going to be our bells there. So we take the log of this, and this becomes 11.2 bells. Okay, so I should get rid of that B right here. That's not correct. You take the log of that, and that'll give us our bells. Now, why do they do that? Well, mainly because if you tell somebody in the general public 1.59 times 10 to the 11 is a ratio, they have, a lot of people didn't have an idea back then, and it's kind of still that way now. So we use logarithms to try to bring it home as to something that people can grab onto. It turned out that was not as good a reception as they hoped. So they went ahead and chopped this up into 10 bits, and so they called this then a decibel. And decibel means 1/10 of a bell. So we chopped it into 10 parts, so that means we just simply multiply this by 10, and then we get 112 decibels. Okay? So 112 decibels is pretty loud. In fact, there's a couple of charts in the book that you are going to need to refer to. One is on page 500, the other is on page 503, in which case you'll see the range. And I believe it says that 110 decibels is pretty much where a rock concert is located for that. And so that's where they come up with it. So the comparison that we're going to use for this to find the decibels is going to be 10 times the log, 10 times the log of I over I-O. Where that becomes then equal to 10 times the log of I over 1 times 10 to the negative 12 watts per square meters. Okay? So,